of the experimental evaluation that we did of multiple heuristics for doing pre-allocation instruction scheduling. And I will give a brief summary of the results. Then I will spend most of the lecture trying to describe our branch and bound algorithm, the algorithm that computes the optimum solution, the optimal solution. Okay, so we did an experimental evaluation of multiple heuristics by looking into spec CPU 2006. So spec CPU 2006 is a set of benchmarks, which is the standard for evaluating CPU performance. And it has two sets. It has the int set of benchmarks. There are 12 benchmarks of int, or 12 int benchmarks, and 17 floating point benchmarks. By the way, which ones do you think, which of these two groups, the int benchmarks and the floating point benchmarks, which one do you think will have higher register pressures?
Floating point.
Yeah, the floating point, because the floating point benchmarks are scientific programs that do a lot of computation, while the int benchmarks are non-scientific applications. Yes?
Are floating point calculations also more intensive too, or?
Yeah, they have lots of floating point computations, but it's not floating point versus integer as much as it is scientific versus non-scientific. So integer benchmarks, they have a lot of control flow, like if-else, which means that you don't have a whole lot of computation going on compared to the floating point benchmarks. So if your program has lots of if-else, lots of conditioning, handling multiple cases and conditions, as opposed to doing a long sequence of computation. So long sequences of computation with lots of dependencies, those create higher register pressures. So we will focus on the floating point benchmarks. The floating point benchmarks, there are 17 programs. These 17 programs have 17,000, or exactly 17,188 functions in them. So it's on average, each program has 1,000 functions in it, roughly. Compilers, in general, and LLVM is no exception. LLVM does register allocation to one function at a time. It does the allocation for the local variables. It does it for one function at a time. So for an application that has 1,000 functions in it, there will be 1,000 different function allocation invocations of the register allocation algorithm. And for each of these invocations, the register allocator is going to do the allocation, and then it may generate a number of spill instructions. So we just modified the register allocation code to print the number of spills. So we printed the number of spills for each function, and we did that by applying different heuristics. So we did a study like this. We have functions, f1, f2, f3, f4, and we have heuristics, heuristic number 1, heuristic number 2, heuristic number 3. So for each heuristic was applied to the entire benchmark, and we looked at the number of spills that got generated. So if we get something like 5, 6, 10, and 13 for this heuristic. For another heuristic, you may get something like 7, 6, 10, and 15. For another heuristic, each heuristic is going to give you a different number of spills because it's going to change. These heuristics are instruction scheduling heuristics. So we are studying the impact of changing the order before we do register allocation. So we're not making any change to the register allocation algorithm. Same register allocation algorithm, but we are trying different scheduling heuristics. We are only playing with scheduling and studying the impact of different heuristics. Heuristic 3 may give you, 6, 12, and 12. So in this case, you can compute, for example, the minimum for each function. For each function, I know that for function 1, I can get 5 spills. So 5 spills is the best that I got among these heuristics. For function 2, I got 6. For function 3, I got 10. And for function 4, the best that I got is 12. Okay? So here, if you sum these minima, if you sum the minima, you'll get here 11, 10, 21, 31, 33, right? So this is, 33. 33, this is the sum of minima. What does this sum of minima mean? Well, it means, how does the sum of minima relate to the optimal number of spills that we can possibly get?
Usually will be greater than or equal to the
Yeah.
optimal.
So the optimal is going to be less than or equal to the sum of minima. So optimal is less than or equal to sum of minima, which means that the sum of minima is an upper bound on optimal. Sum of minima is an upper bound on optimal. Now, then we evaluated each heuristic relative to the sum of minima. For example, for this, this is 11, so this is going to be 34. So this means that on average, this heuristic gave, an extra spill relative to the sum of minima. And we also looked at, for each heuristic, the percentage of time this heuristic was optimal. So let's write it here. Percentage optimal. So for this, or percentage at minimum. This is the percentage, what percentage of functions, for what percentage of functions this heuristic gave the best result. So heuristic number 1 gave the best result for this.
100%?
For this, and this, and this, but it did not give the best result
I
for
didn't
this.
see the last one.
Yeah. So for this heuristic, it's like 75% of the time, it gave the minimum. This heuristic, here it's not the minimum, here it's the minimum, here it's the minimum, and here it's not the minimum. So this is 50% of the time. Okay? So these are not, this is a small set of heuristics and functions. So we did a study using the 17,000 functions and about a dozen heuristics. Okay. So we looked at those results. I will give just some a sample of the results. So we did heuristic and percent at minimum, percentage of functions at minimum, and we also percentage increase or percentage extra spills relative to the sum of minimum. Spills relative to sum of minimum. So let's look at some heuristics that let's look at critical path with LUC. So do you guys remember what LUC stands for?
Last use count.
Yeah, last use count. So critical path is a standard term. So you'll see it in different books and papers. but LUC is a local term. It's not a standard term. Okay, and we have LUC CP. So now in terms of spills and percentage of functions, so let's see the numbers for critical path. So critical path gave the minimum for 47% of the functions. Now CPLUC, do you expect it to give a higher percentage or a lower percentage? Higher
because it
percentage.
has a secondary
Yeah.
priority
Yeah.
also.
Exactly. So CPLUC gave 50%. It's not much higher. And LUCCP gave 55%. So even this heuristic, it's 45% of the time it wasn't giving the minimum
Right.
spill count. Extra spills relative to sum of minimum, for critical path it was 16%. So it gives 16% more spills relative to the sum of minima. And for CPLUC it gave 14%. And for LUCCP it gave 7%.
Professor,
Okay. Yes.
shouldn't the sum of minimum be a lower bound on the optimal? Because that's the minimum number of spills that even the best algorithm could give you.
Well, that's the best in the set of algorithms that we tried, right? But these algorithms, none of them is optimal.
Right.
So there may be an algorithm. So if we got 5 here, it doesn't mean that we can't find an algorithm that will give 4 or even 0.
Okay.
There may be an algorithm.
So optimal is just a conceptual algorithm that we are considering. The one that-
Conceptual because none of these are proven
Right,
optimal, so
right.
we can't treat them as such
Okay, okay.
because none of them is proven
Right.
to be optimal.
Yeah.
So this sum of minima is an upper bound on optimal. The optimal will be,
Less than.
at least as good as this, but probably better. We expect it to be better. Okay. So it's just, what does this, these results are as expected because LUC, this is the register pressure. It treats register pressure as a primary objective. So it tries to close as many live ranges as possible. And that's why it gives better results. It only gives 7% above the sum of minimum. Okay. This means that the gap between LUC and optimality, the gap between LUCCP and optimality, is it going to be greater than 7% or equal to 7% or less than 7%? In other words, is this 7% an upper bound or a lower bound on the gap between this and optimality?
Upper bound.
It's an upper bound.
Is it
Lower.
on the gap? So what's the gap? The gap between this and optimality. So if
It should be.
Optimality would give you 0% extra spills relative to sum of
Yeah,
minima.
it would be.
Or even lesser than that.
yeah,
Yeah.
So the upper bound would be 7%. So it could be 0 or even lesser than that. Extra spills.
okay, is
Lower bound,
again,
it's a lower bound.
it's a lower bound. Yes, this is a lower bound. Lower bound
Okay.
on the gap between LUCCP and optimality. Why a lower bound? Because this is relative to SOM, sum of minima, and sum of minima is an upper bound on optimality. So optimal is going to be possibly less than this. So optimal could be 30, it could be 25. So if the optimal is 25, then this 7% will go up. So it's not 7% above optimal, it will be 8% or 9% or 10%. So what we are measuring here is that are lower bounds on the gaps between these heuristics and optimality. Okay? Anyway, so this is just the experimental study that we did to see if it makes sense, to do some further work in this and try to look for a better algorithm. Is the gap between existing heuristics and optimality, is the gap significant enough to justify looking for a better algorithm or not? So that was the main question that we were trying to answer.
So I guess the other part of the equation would be increasing the instruction level parallelism.
In fact, these heuristics, this heuristic, it still tries to balance register pressure and ILP, but it considers register pressure to be a primary objective and ILP as a secondary objective. This does the opposite.
Yeah, because of the out-of-order processors that we use nowadays.
But even if you ignore ILP and only look at register pressure, there is no known heuristic that gets you close to optimal. Okay. So this study, by the way, included all the heuristics that were implemented in LLVM 3.3, but not at the current low level, at a higher level, which was the selection DAG level. The selection in the earlier versions of LLVM, instruction scheduling was done at a higher level. Now it's done at a lower level. And we don't know, at this point, the current heuristic in LLVM, we don't have numbers for it. We don't have such numbers for it. How far it is from optimality, we don't know. Okay, so this is just the experimental study. Let's now focus on understanding the branch and bound approach. So the branch and bound is an algorithmic technique. Generally speaking, branch and bound is an algorithmic technique It's an algorithmic technique that searches for an optimal solution by exhaustively searching the entire solution space, but it employs some pruning techniques that will allow it to exclude certain options as early as possible. So it doesn't explicitly look at all solutions. It may exclude or rule out some of the solutions using certain logical arguments, as we will see. So let's look at the example that we looked at last time, which is this example. So we will apply branch and bound to this. See. So this is the example that we considered last time. And for the time being, let's ignore instruction level parallelism. Let's assume that all what we want is minimizing register pressure. So for now, ignore ILP and latencies. So I didn't even put the latencies, but we still have precedence constraints. So we no longer have latency constraints, but we have precedence constraints, meaning that we still, C still cannot be executed before A and B. C is still dependent on A and B. So you cannot do C before A or B. You have to do A, B, then C has to be done after A and B. So you have to honor the precedence constraints. But we still honor precedence constraints. Now, our branch and bound approach to this problem first finds a heuristic solution. So the first step is find a heuristic solution. Find a heuristic solution. So use some heuristic to find a heuristic solution. So let's assume here that the heuristic solution is what was the heuristic solution that we got from critical path? So that was E, B. Oh, let's put it here. E, B, D, A, F, C, G. So this solution is A, B, D, A. What's the peak register pressure of this solution? So what's the peak register pressure? So our register pressure is going to be for now. After doing E, it's 1. Then with B, it's 2. With D, it's 3. With A, it's 4.
Yeah,
so it gets
4.
then it drops. So the peak register pressure for this heuristic solution is 4. So we computed some heuristic solution. We don't know if it's optimal or not. Sometimes we do the exhaustive branch and bound search only to discover that the heuristic is optimal. So sometimes, the only purpose of the exhaustive search is to discover that the heuristic is optimal, or to prove that the heuristic is optimal. Now, let's assume that our objective is to minimize register pressure. So we don't care about ILP for now. So our objective is minimizing our objective, or our cost function. Our objective is minimizing register pressure, or the peak register pressure of the schedule. Minimizing the peak register pressure, or PRP. So we are looking for a schedule with PRP less than 4. So let's see how branch and bound works. So branch and bound can be represented by a decision tree. So you have your root node. And at the root, how many options do we have now in this?
A, B, D, E.
We have 4 options initially, right? We have exactly 4 options. Now let's assume that we sorted them by according to a certain criterion. Well, in this case, maybe critical path. In critical path, if we refer to the previous lecture, so the critical path of this was 5, I believe, and this was 4, and this was 3, and this was 2. So suppose that they are ordered E, B, D, and A. So we first consider E. So after considering E, we go with this choice. So now we are at this node. Now our register pressure, our peak register pressure here is 1. or let's use a different color. So peak register pressure equals 1. Then we have three options, B, D, or A. So suppose that we do B. So now our cost, peak register pressure equals 2. Now we have two options, either D or A, right? And let's pick, in this case, let's pick D. And with D, we get a register pressure of 3. And then after doing D, we have the option of doing
A or F.
A or F. So suppose that we did A. Now if we do A,
We get 4.
our register pressure becomes 4. Or our peak register pressure becomes 4. Now this means that our register pressure is already 4, and we're trying to look for something that is better than 4. So in this branch and bound approach, our best schedule is initially the heuristic schedule. So our best cost, or the initial best cost, equals 4. Now this 4 is the peak register pressure at this point, but it's also a lower bound on the cost for any schedule that we may find below this point, right? It is a lower bound here because of the nature of our cost function. Our cost function is a peak.
Right.
So the register pressure below this point may drop below 4, but our objective is the peak. Our objective is minimizing the peak. This means that the peak register pressure here is a lower bound on the peak register pressure of any schedule that we may find below this node. This means that based on this lower bound, we don't need to explore the tree any further below this point. We don't need to explore any schedule. So we did not even get to a complete schedule here. So we say that we prune the subtree below this node. Why did we prune the subtree below this node? Because the lower bound is already equal to the cost, to the best cost that we found so far. So we prune here, let's write this. We pruned the subtree below the current node because the lower bound at this node is greater than or equal to the best cost found so far. So this is the general idea of branch and bound. You keep track of the best cost that you found so far, which is in our case the heuristic.
Yep.
Okay?
4.
And at each node, you compute a lower bound on the best cost of any solution that you may found below this node. And if the lower bound is not any better than the best cost that you have so far, there is no point in exploring this subtree any further. This is the key idea of branch and bound, and that's why it's called branch and bound. So we are branching, and we are computing bounds, and based on these bounds, we are doing pruning of the tree. So now, since we don't have to explore this any further, we are going to backtrack. But we don't backtrack all the way to the root, we just backtrack to the last node. So we backtrack here and see if there is another option that we have. So do we have other options at this node?
F.
Yeah, we have F. So in this case, we consider F. So this is another option, and this leads to another node. Now with F, what will the register pressure, the peak register pressure be at this point?
It stays at 3, I think, because
No, F
No,
is
no,
going to
it goes-
close
it goes-
2 and
yes.
open 1.
Yeah, it's a multiply, so it's gonna go down to 2.
Yeah, it will go to 2 because it will close
those two.
this and this, and it will open a new one, so it will be 2. Now, in fact, we shouldn't label this node with 2. We should label it with 3, because the peak register pressure
Okay.
equals 3.
But the
Why 3?
current-
Because we are keeping track of the peak. It's not the current register pressure that we are interested in. We are interested in the peak of the partial schedule that starts from the root node to the current node. So look at this path, tree path. This represents a partial schedule. So what we track here is the cost of the partial schedule that is represented by the path from the root to the current node. Okay, and this is 3, so it looks like we can find something better than the best known cost, and in this case we will indeed, because after F we'll have to do A, right? We cannot do C, so we'll do A. And with A,
It still remains.
Yeah, it'll go back up to peak 4,
yeah,
right?
so with A, the register pressure, no, it will not go to 4,
Wait,
because
what's 3?
remember that peak register pressure is 3, but current
Oh, yeah. Current is 2.
register pressure is 2. So here the current is going to be 3 and the peak will be 3. So the peak register pressure equals 3.
It'll just remain 3 till we reach the end. Yeah.
Yes, and here we are almost done because after doing A, we
It's the end.
we have to do C. The only option is C, right? We don't have any other options. So we do C, and the peak register pressure will stay at 3, and then after C, we do G, and the peak. The register pressure is going to drop, but the peak will be
3.
4. It's
Or
3.
4. 3. Yeah.
Now, here at this point, we constructed a complete solution, a complete schedule. So now we have a complete schedule. And since the cost of this complete schedule is better than the current best cost, this becomes the best solution found so far. So now we will update the best solution found so far because we have just found something that is better than the initial best solution. So this is now our current best solution. And our current best cost is now 3. So after this point, we will only be interested in schedules with costs less than 3, if there are any. In this case, it turns out that there aren't, but we haven't proven this. So in a branch and bound scheme, we will keep searching until we find something that is better than 3, or we prove that 3 is the best that we can find. So we are not done yet.
So we backtrack all the way up now.
Yeah, well, we backtrack, yes, but
To B.
how do we backtrack? So if we backtrack here, do we have other options?
No.
No, the only option that we had was G.
Yeah.
Then we backtrack here.
You backtrack all the way until you get to peak register pressure too.
Yeah. So we backtrack to this, and the only option that we had, C. Then we backtrack to this, but here our peak register pressure, yes, is already 3, so it's not interested. It's not interesting. So we backtrack. So we just backtrack to the
This point.
deepest node that has a cost
Lesser than.
less than what we are interested in.
Mm-hmm.
Than what the best that we have so far. And then At this point, one of the options was D, so we will consider other options. What are the other options besides D?
A. But that'll
A is
add.
the only other option, right?
Yeah.
Here. So we did E and B. E and B are done. And we are considering another option besides D, and that's going to be A. Okay?
But-
And with A, our register pressure,
It's 3, right?
Yep.
yeah, it's in our peak register pressure, peak
Becomes 3.
register pressure equals 3. This means that it's not any better than the best that we have, so we just backtrack. And this is, think about how many solutions we have excluded by backtracking here. So there's a whole subtree below this, right? So there's a
Yeah.
whole subtree that we just excluded by backtracking. And why did we backtrack? Because we are already at 3.
Yeah.
Anything below this is going to be 3 or worse.
Yeah.
So we just backtrack to this. And now, do we have other options?
No.
We don't have other options. The only two options were D and A. So we backtrack to this.
Yeah. For me, you could do.
And we have other options. So we have uh,
A or D.
we have, for example, E, B, and D, maybe. And with D, we have options B and A, but either option will get us to 3, right? If we do B or A, either one of these, but we have F as well, right? With E and D, we have F. So we have B and A and F. So those B and A are going to lead to 3, and we will prune. So we'll prune this, because now we are at 3. Now with F, our peak is 2. Okay? And here, in this case, we can continue exploring this, but we will eventually, get to a 3, and a 3 is not any better than the best that we have, so we will backtrack. One other pruning technique that we do, so you understand now this basic pruning technique of keeping track of the peak register pressure, in this case, which is a lower bound, and if you get to something that is not better than the best cost that you have, then you prune it. Now, what if I would like to, I think let me draw another 3. So what if we get to this point where this is, we have done this, A, B, and at some point we will explore B and E.
Same thing.
So the idea is, this is something that we have explored, and when we got to this, E and B, the best solution below this is this solution with cost. So we can label this node as, it has a solution below it, and best solution has cost equal to 3 for this node, right? Now, in this process of doing an exhaustive search, at some point we will get to this point where we are considering doing BE instead of EB. Now the point is that we can make an argument where we compare these two and conclude that below this we will not find anything that is better than
It
that.
produces the same subtree as the other side.
Yeah, and how? So we need a precise argument for this. This is what we call our history domination technique. Why history domination? Well, the idea is that this is a history node, so we will store this in a history table in some kind of data structure. We'll talk about the details of this later, but we store this in some kind of history data structure. So this is there with all the information about it. So this is a node that we store in a history table, and this is a node that we are currently examining. So we would like to compare the current node with the history node. And if we conclude that the current node, that below the current node, we can never find anything better than the best solution below the history node, then we will prune the whole subtree below this, and we don't need to explore this any further. Now the argument here, so you need a precise argument to prove that you will not find anything better. So why EB versus BE? So generally speaking, we look at what we call similar nodes. Similar nodes. So two nodes are similar if the partial solutions for these two nodes are permutations of the same set of instructions. So let's focus on, let's make sure that we all understand the terminology. So the partial solution for this node is EB. So this is a partial solution or a partial schedule. And the partial schedule for this node is BE. So these partial schedules are similar because they are two different permutations of the same set of instructions.
Mm-hmm.
Okay. Now, the first thing that we should consider in this comparison is the partial cost, or the cost of the partial schedule. Cost of partial schedule. So let's call it the partial cost. And the partial cost in this case is 2, while the partial cost, so this is not a complete cost, also 2. So they have the same partial cost. So the argument is the cost of any solution below this node is going to be the maximum of the partial cost and the cost and the highest register pressure at any node below this node. Okay. But now, is there any solution, any permutation of the remaining instructions that is possible here but not possible here? Is there possibly any
No.
permutation of the remaining instructions? So in this case, the remaining instructions are all instructions except
BNE.
BNE. So because we are only looking at precedence constraints, and because what has been scheduled here is the same as what has been scheduled here, so any permutation of the remaining instructions that is possible here was possible here.
Yeah.
What does this mean? It means that the best that we can find here is the same as the best that we can find here, and then the total cost of the solution will be the maximum of the register pressure of this part of the schedule, which we call, by the way, the which we call the suffix solution. So this is the prefix of a schedule, and whatever we compute here is the suffix.
Mm-hmm.
So the point is that any suffix below this is not going to be any better than any suffix below this. And the prefixes have the same cost, so there is no way we can find something better below this point. So we just prune away, and there is no need to
Yeah.
to consider this any further. So this is how we managed to explore the entire solution space relatively quickly. So it's relatively quickly. So it is still
Yeah.
slow. It still considers more solutions than
Then,
a heuristic.
Yeah.
In a heuristic, all the heuristics that we have presented are what we call greedy heuristics,
Greedy, yeah.
where we just make a decision, make a choice, and commit to it. We never undo a decision that we make. So we make a decision, we stick to it, and we are always making progress. We never backtrack in the heuristics. Here, there is backtracking. So we backtrack and we undo decisions and we consider different solutions, but we try to do it as efficiently as possible, and we try to detect as early as possible that below the current node, we will not find something that is better than the best that we found so far. This is the idea of our approach. Okay. And the good thing here is that we set a time limit. So for practicality, we set a time limit, and if that time elapses, then we just stop and we take the best that we found so far. And the chances are that within this time limit, we will find something better than the initial heuristic, even though it hasn't been proven optimal yet. But in many cases, we find something that is better than the initial heuristic. So from a practical point of view, you just set a limit, a reasonable limit on how much time you are willing to give to this, and take the best that you can find within this time limit. Yes.
The time would definitely be lesser than a greedy algorithm, right? Even if it were to prune just a couple of subtrees away, it would still shave off a couple of time minutes from relative to a greedy heuristic.
Oh, relative to greedy?
Yeah.
It's faster?
Yes.
No.
The branch and bound, I'm assuming.
It will always be slower.
Yeah, because you're exploring more nodes. than
Yeah,
the
you're
heuristic.
exploring more nodes. So greedy is just, you make a decision and you stick to it.
Yeah.
You commit to it. You never undo. You never backtrack.
Okay.
So that's what greedy
Yeah.
is. So this is definitely
Slower.
slower than greedy all the time, but it's more likely to find better solutions because we are backtracking. So we are trying to make it, we know that it's slow, but we're trying to make it not too slow.
Yeah.
We're trying to bring it to the acceptable limits, the acceptable limits in terms of time. So this is the whole. Of course, this is the basic algorithm, so there are more details that we can discuss next time. In fact, next time we'll see how we can do this, how we can combine ILP and register pressure, how we can find something that balances ILP and register pressure. Any questions on today's lecture? Yes.
Well, not really a question, but a comment, because I took AI, and a lot of the history tables and stuff that we use in Minimax to find the best move for an opponent to do is similar to the stuff that we do here.
Okay. Yeah,
So-
that's good. Yeah, in fact, this work has got the interest of many people in AI. Yes. So many people in AI, have shown interest in this, and we have citations by people working in AI, and if you have ideas that we can use to enhance this. So this is not the best, by the way. Next time I will present ideas for further enhancement, but that's not the end of the story. You may have other ideas that will further enhance this.
Yeah.
Okay.
Are we allowed to take multiple passes over the schedules that we take? Or,
Yeah, well, it all, you have a time limit,
Right.
and within that time limit, try to do the best that you can within a given time limit. Any other questions? All right, so I will